Here's a relatively straightforward thermodynamics problem which looks at energy conversion. So we're dealing with a vessel which is moving with a velocity v at first, and then when the vessel stops, all that kinetic energy gets converted into, well, something, and we'll look at what exactly that is. And that will result in changing the temperature of whatever's inside the vessel, of that ideal gas. Now, this is as I mentioned earlier, it's a straightforward problem, and if you have any similar questions that you'd like to see on this channel, maybe you're doing thermodynamics as a first-year engineering student, or maybe you're doing this in high school, whatever the case, let me know in the comments. So, in the first instance, we're dealing with a vessel which is thermally insulated, so that's important to note. So I'm going to draw that like this. So sort of like have two layers, and we have the thermal insulation in between, and then here inside there's the gas. And we know the gas has a molar mass which is equal to capital M, and we know the ratio of specific heats is Cp over Cv, which is gamma. So let's actually write that down. We have Cp over Cv is equal to gamma, and it moves with a velocity v. So at first this is traveling to the right, let's say, or in any direction, doesn't really matter, with a velocity v. So that allows us to find the kinetic energy, which is 1/2 mv squared, like this. So that's the kinetic energy of the gas. And then when it suddenly comes to rest, we can actually apply the first law of thermodynamics, which is Q equals to W plus delta U, to figure out what happens to this kinetic energy, basically. So first of all, this vessel is thermally insulated, which means that there is no heat input from the outside. Okay, so the value of Q is going to be 0, and this turns into 0 equals W plus delta U. And what we actually have to find, which is the gas temperature increment, which is also related to the change in internal energy. So we can take out internal energy, and that's minus W, like this. And then we can say that the change in internal energy is M times CV times delta T. And I think for the purposes of this question, we actually look at, so we're not actually dealing with mass, we're dealing with the number of moles, right? So this should be N, like that. And the change, so this used to be delta U, and the work done, or minus work done in this case, is given by minus, and then we have the fact that the work done is the change in kinetic energy. So let's write it as the change in kinetic energy. And then we have number of moles times Cv times delta T is equal to minus. Now the change in kinetic energy, as usual, is final minus initial. So it's 0 minus 1/2 mv squared, like this, which is 1/2 mv squared. So 1/2 mv squared is n Cv times delta T. Now keep in mind that this m, this mass, is the mass of the gas, which is the same as the number of moles times the molar mass. So if we rewrite this here on the right, we have n, we have Cv, we have change in temperature is 1/2 n m times v squared. So we can cancel the number of moles, and we end up with the change in temperature, which is, let's see, we have 1/2 molar mass v squared over Cv. And we can leave it as it is, or we can express Cv in terms of other things, like gamma and the universal gas constant. So that's 1/2 mv squared over, and instead of Cv, I'm going to write that as R over gamma minus 1. So delta T is going to be gamma minus 1 over 2 mv squared over R. Now, obviously, this question doesn't actually use any numbers, but if you had numbers, you can put them in here, and that would give you a temperature increment, and that would be in Kelvin. And that's the end of the question.